Hello and welcome to my presentation. My name is Rahmat Haydari, and I'm going to present a paper we've written with my co-authors, Frederick Geth and Arpan Korada, on four-wire distribution power networks with a sparse neutral groundings and the computational analysis of impedance transformation models. So first things first, what are distribution networks? So the power system has different voltage levels and basically can be divided in transmission and distribution. Transmission network is basically responsible to deliver the power generated from the generator over the long distances at high voltages to the distribution network, which is at lower voltage level and where the customers and players are connected to. And the network is more than three-phase cables, transformers, load generators. It has other components such as feeders, which are from MV, LV transformers, service line branches to the customers, overhead lines and underground cables, which we're gonna focus on in this paper, and customer mix, which can be residential, commercial, and etc. The low voltage network has different designs. For example, US has widely different design approach to MV/LV distribution grid, as in they have 120 volts and they're mainly split phase network, whereas Australia has distribution grids which are more similar to European networks, as in there are 400 three-phase or 2030 volt single phase networks. Low voltage networks, we can look at them as mathematical graphs and basically consider buses and branches as graph elements. So buses have nodes for each of the conductors. So have A, B, C, which are phase conductors, and then N is the neutral conductor and G is the ground conductor. Ground conductor is a ground conductor voltage is assumed to be zero, and everything is then defined relative to that. But in most networks, we can assume that the ground is generally implicit. Then there's also three-wire networks, which they don't have neutral, but for these networks, when we don't have neutral, the loads and generators need to be connected in delta mode. So just to mention, this is not the kind of network we're looking at this work. There's also single phase networks, whereas there is a neutral between, and there's a neutral connection, and we also consider this type of network in this study as well. Next, we have branches. For example, three-wire branches have 3x3 impedance and shunt admittance matrices, and these shunts are the same for both sides. Yeah, and the impedance matrix is above all the matrices are real and symmetric and positive, definite. So these three matrices include 2x3x9 real parameters per branch, which need to be identified in order to model the network. With 2 is the real and imaginary part of these complex elements. Then there are 4-wire branches, which have 2x3x16 real parameters per branch, which the extra parameters are due to the extra row and column due to the neutral voltage and current in the network. Then there is network neutral grounding configuration variance. So neutral ground. We have different types of networks, like we have radial or meshed, and neutral can be grounded either at a single point or at multiple points in the network. For instance, in Australia, UK, and US, it's common to have multi-grounded networks, whereas in Germany and Belgium, it's common to have single-grounded networks. And they have an impact on the way you need to model a network. Next, we look at the branch impedance models and the transformation. It is not easy to obtain impedance models, mainly because it is hard to measure impedance without taking the grid offline. And also, we obtain impedance from first principles, that is Maxwell's laws, which John Carson's approximated them. We require material properties. For overhead lines and single conductor cables, we need configuration of conductors in space relative to the ground. However, for bundled aerial or underground cables, we know the parameters when they leave the factory. So as I said, for full-wire networks, if we have geometry and DC resistance, we can use Carson's equations or finite element to derive the 4x4 impedance model or impedance matrix, which includes self and mutual impedance values. Then we can give this model to the 4-wire solver, which then includes bus voltage variables with the neutral terminal and also branch flow variables with neutral current. However, legacy power solvers do not support 4x4 matrices and perform a transformation to change it to 3x3. And cross reduction is a solution that is commonly used, where the impedance matrix is 3x3, and the bus voltage doesn't have the neutral terminal, and the branch flows don't have the neutral current. However, the strong assumption here is that the neutral is perfectly grounded at every bus in the network, which in places like Germany and Belgium, the neutral only tends to be grounded at the substation. And also perfect grounding is impossible, and grounding is never done at every bus. On top of that, having a non-zero conductor voltage decreases the power you can transfer before you hit the limits. So a current reduction approximation or transformation can lead to significant underestimation of voltage magnitude problems and over or underestimation of voltage unbalance in the system. So being conservative doesn't help here. So this transformation should be avoided if you have the data and the grounding is sparse. And the alternative transformation we propose is we call it phase to neutral transformation. The assumption is that the network is sparsely grounded, and this transformation is exact for single grounded networks. And you can see the transformation on the right here. Then there is also a modified phase to neutral transformation, which on top of the which is built on top of the phase neutral transformation here. So in just summary of the three transformations, the cross reduction assumes neutral voltage is 0 at all the buses. Phase neutral transformation that we propose assumes that the ground current is 0. And modified phase to neutral assumes ground current is 0, and also there's no mutual impedance. So then we move on to performance of the proposed transformation. On the right, here you can see the voltage magnitude drop along the feeder and the comparison between the 4x4 impedance matrix, a network with 4x4 impedance matrices, and the network with 3x3 impedance matrices derived from phase neutral transformation. And as you can see, the this network is single grounded, and as you can see, the voltage magnitude calculation is precise. So it's there's no inaccuracy in this transformation for a single grounded network. We then performed the same comparison for similar networks, 128 similar sized networks, which are also single grounded. And as you can see, there is no difference between the transformed network model and the original 4x4 network model impedance, the original network with 4x4 impedance matrices. Then the next step was to just basically compare the other transformations with the original network and see how they perform. So as you can see, the cross reduction has some voltage magnitude difference. So it's non-zero and it's inferior to the phase neutral transformation. And modified phase neutral is yeah, not performing as well. So in conclusion, the proposed phase neutral transformation is precise for single grounded networks and reduces the size of the branch matrices from 4x4 to 3x3. And the network can be the optimization can be solved with 3 voltage variables per bus rather than 4 variables per bus. This transformation is distinct from cross reduction, as in it can facilitate modeling a sparse neutral grounded networks, whereas cross reduction requires all neutral at all buses to be grounded. This transformation also establishes neutral voltage shift rather than assuming the neutral voltage to be 0. We then validated the equivalence of the phase neutral transformation with respect to 4x4 impedance model via simulations in OpenDSS across 128 single grounded networks. This transformation delivers minor but non-negligible computational benefits to the unbalanced power flow optimization problem compared to the 4x4 impedance model, which is valuable in large-scale problems. Thank you very much for your time and attention. We can be reached out at the email addresses provided here. If you have any questions, happy to answer your questions. Thank you.